In the deep ocean, individuality fades. Bathyphysa sibogae, a siphonophore seldom filmed and almost never captured, lives as a colony that behaves like a single creature. Each segment, called a zooid, is a specialized life form with its own task: feeding, reproduction, propulsion, or defense. But they are all genetically identical, locked into a collective so extreme that no zooid can survive alone. Biology usually favors independence. Bathyphysa sibogae thrives by abandoning it entirely. The organism's most surprising trait isn't its length or its ghostly transparency. It's the structural lattice beneath the gelatinous surface. High-resolution scans from deep-sea ROVs show that the stem connecting each zooid contains microfibrous tension bands, elastic threads arranged in spirals similar to plant xylem. This spiral architecture lets the colony stretch without tearing when pressure shifts rapidly. It's a natural deep-sea suspension bridge, grown without a plan, yet mathematically perfect. Unlike most siphonophores, B. sibogae has unusually large nectophores, swimming bells, that coordinate propulsion through synchronized pulses. But synchronized understates it. Ion channel mapping suggests the pulses form a distributed rhythm controlled not from a central node, but through wave propagation across the colony, like a stadium wave executed by tissue. Each zooid delays its contraction by milliseconds, creating a peristaltic motion that moves the entire organism forward with minimal energy. Evolution built a living conveyor belt. The feeding structures hold an even stranger secret. Along its tentilla, the fine, branching feeding threads, lie clusters of C. nidocytes arranged in helical lines. This isn't random. The helices match the colony's natural torsion during movement, ensuring that the stinging cells always face outward even when the colony twists. It's the biological equivalent of a camera stabilizer, except made of cells that fire harpoon-like capsules. What sets Bathyphysa sibogae apart from other siphonophores is its ability to reassign function. When a feeding zooid is damaged, the nearest reproductive zooids temporarily increase metabolic activity and change their nutrient transport pathways to compensate. This reversible specialization hints at a genetic regulatory system more flexible than most animals possess. A colony with distributed roles behaves like a decentralized economy. Resources shift to where they are needed without a leader. To locate prey, B. sibogae doesn't rely only on chemical cues. Its stem contains vibration-sensitive cilia capable of detecting the turbulence signature of swimming organisms. Turbulence has texture, and B. sibogae distinguishes between the smooth wake of small plankton and the irregular push of larger crustaceans. That sensory precision allows it to deploy tentilla only where they will matter, conserving energy in an ecosystem where calories are rare. Albert Einstein once remarked, "The whole is more than the sum of its parts." Bathyphysa sibogae exists as proof. It is a collective shaped into a single intention, a living argument that individuality is optional in evolution's toolkit. If this deep-sea giant fascinates you, support the channel with a like, subscription, and any encouragement. Your support helps bring rare creatures of the abyss into the light.